Hi there, this is Penelope. This is a video, actually a post video of the class that was available to the students 5th of April 2023. So this is a video made after the class. The notes for the class are on Podia. This is a video for those that actually missed the class and need a bit of a hand rather than just the notes this time. So before we got into the material, we looked at Pascal's triangle. Now, Pascal's triangle has nothing, in a sense, to do with complex numbers, trigonometry. Its place is actually in algebra. But what it is a little trick to expanding brackets. If we have brackets like this, then we can multiply out and if you just notice and note down the coefficients of that, they go 1, 2, 1. Now, if we were to do a plus b cubed and multiply it out in full, we would get a cubed plus 3a squared b to the power of 1. I don't need to write the 1, but I did. And again, I'm just going to write down the coefficients of each of those terms. So it's 1, 3, 3, 1. Now to do a plus b to the power of 4. Now, you might begin to see a pattern there when I now write out the coefficients again. And then 4, and then 1. And if I do one more, you should be able to pick up the pattern. I'm just going to have to write this a bit smaller so that I don't run out of space. So it's a to the 5 plus 5a to the 4 b to the 1 plus 10 a to the 3 b squared plus 10 a to the 2 b cubed plus 5a b to the power of 4 plus b to the power of 5. Now, I didn't quite make it in the space, but I'll still write down underneath the coefficients. So it was 1, 5, 10, 10, 5, 1. And I can go on doing that. Now, look at that. The pattern is that down the outside of this triangle, there are 1s. So that each of the expansions starts with something and the coefficient is 1. It ends with something, the coefficient of which is 1. Now let's have a look at line 2, so the expansion of a plus b cubed. To get from the previous line, 1 plus 2 is 3, 2 plus 1 is 3, and we write a 1 at the end and the beginning. Next line down, we write a 1 at the beginning. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, we write a 1 at the end. Next line, 1 at the beginning, 1 at the end, then 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and then 1. So it's just a pattern of the coefficients when you're expanding brackets. Now, the other thing to look at too is have a look at the powers. Once we've sorted the coefficients, have a look at the powers of a and b. So the first one, it is 5. Then it's a to the power of 4, b to the power of 1. So it's 4 and 1. Then 3 and 2, 2 and 3, 1 and 4, and then 5. So these are the powers. If we put in things to the power of 1, every occurrence has an added sum of the powers to 5. Now, we can't actually combine those and add the powers, but it's just the way we work it out. So I can, just without really even thinking, write down this. It would be a to the power of 6, then 6, a to the power of 5, b to the power of 1, plus 15, a to the power of 4, b to the power of 2, should put my plus in there, plus 20, a to the power of 3, b to the power of 3, plus 15, a squared b to the 4, plus 5a b to the 5, plus b to the power of 6. All I'm doing is I'm just following the pattern set up by Mr. Pascal, just of the coefficients, and knowing that my powers, the a powers go down, the b powers go up. Really, that first term has b to the power of 0, but we don't need to worry about that. Now, this is going to help us shortly when we look at something that is to do with trigonometry, where we're multiplying out brackets. We're taking a complex number, cos plus j sine theta, and we are squaring it. Before we start, just remember some things. Just remember that j squared equals -1. Remember also that 2 sine theta cos theta equals sine 2 theta, and that cos squared theta minus sine squared theta equals cos 2 theta. Okay, so we need to remember those facts there. We are going to expand that bracket. We can either just do it normally by FOIL, or we can use Pascal's cheat sheet, so to speak, and we can write that as cos squared theta plus 2j cos theta sine theta plus j squared sine squared theta. Okay, remembering j squared is -1, so this becomes cos squared theta minus sine squared theta plus, and I'm going to put the j right out the front now, 2 sine theta cos theta. All I've done is reorder. Okay, have a look at what we've got then. Let's use some colour. Let's use pink. No, let's use blue. Right, this bit here corresponds to cos 2 theta. So that's cos 2 theta. And again, let's use some colour. Let's look at the next bit where it says 2 sine theta cos theta. That matches up with sine 2 theta. So that would be equal then to j sine 2 theta. Well, that's nice that cos theta plus j sine theta squared is equal to cos 2 theta. So that's the square of a general sort of complex number. Let's do the same for cos theta plus j sine theta cubed. Now, I don't need to do it from the start because I've already got that this is equal to cos theta plus j sine theta times cos theta plus j sine theta squared. And I already know what that last bracket squared is. Okay, so that last bracket we got on the previous line, we got that was cos 2 theta plus j sine 2 theta. Now we need to multiply this out. Now this doesn't fit Pascal's triangle, we just have to work each of this out, but it's a straightforward FOIL, and I'm going to move it over to the left. So it would be cos theta cos 2 theta plus j cos theta sine 2 theta plus j sine theta cos 2 theta plus j squared sine theta sine 2 theta. So I've just multiplied that out. Okay, so the first term is cos theta cos 2 theta. And then, bearing in mind that j squared is -1, I'm going to put that minus sine theta sine 2 theta. And then I'm going to take out the common factor of j, and that leaves me with cos theta sine 2 theta and sine theta cos 2 theta. Well, this would be really nice if we could condense this. And in actual fact, if you look at the formula sheet for the first two, to look for the first terms where we've got cos minus sine. So just a little note down here that cos A cos B minus sine A sine B is equal to cos A plus B. Okay, if we replace A by theta and B by 2 theta, what we've got there in the first two terms, we can combine them to writing cos 3 theta, or cos theta plus 2 theta first up. I guess that would work. Now, if we do the same for cos theta sine 2 theta plus sine theta cos 2 theta, that becomes j times sine theta plus 2 theta. It's the same rule, it's the sine equivalent, sine A plus B rule. Okay, theta plus 2 theta is 3. Now, isn't that handy? That's the same kind of rule as we got from squaring it. When we squared it, we got cos 2 theta plus j sine 2 theta. When we cubed it, we got cos 3 theta plus j sine 3 theta. Okay, let's take a bit of a leap forward and let's write out the rule then that says, generalizing this, that if we have cos theta plus j sine theta to the power of n, that is equal to cos n theta plus j sine n theta. Okay, so I'm going to put that in a square. Like that. So that's just going to help us when we have to do a lot of these. But let's just go back and remember the theorem that we looked at briefly on the previous class, where when we've got things in polar notation, we can square them, because that's just multiplication, cube them, etc. Okay, so this is where it's based on the fact that if Z1 if Z1 equals R1 angle theta 1, and if Z2 equals R2 angle theta 2, that Z1 Z2 equals R1 R2 angle theta 1 plus theta 2. Now, what we're doing when we're squaring it, we're multiplying by itself, so the r's are the same. So we can follow the rule, and it allows us to say that. And for the generalized version, it would be r to the power of n angle n theta. Where we've got to the power of a half, it would be r to the power of a half angle a half theta. Where we've got to the power of a third, it would be r to the power of a third angle a third theta. Now, something we need to think about here. When we find square roots of something, we have to be mindful of the fact that we've got a plus and minus square root. So there are two square roots. Well, here it's kind of the same. And just remembering that when we're drawing a complex number, we could put it in a circle. So here's our complex number here, and our axes are through here. With square roots, there are going to be two of them. So square roots, there will be two. And if we're drawing them, they're going to be equally spaced around the circle. So there's one root and there's the other root. So they're equally spaced. Now, it depends whether we're talking radians or degrees, either 360 by 2 or 2 pi by 2, so 180 or pi. Now, if we've got cube roots, so say we have our first one here, the next one's going to be there, and the next one would be there. So they are equally spaced. 360 divided by 3, or 2 pi divided by 3. So we've got three roots. When we've got the fourth root, to the power of a quarter, we would have 4 roots, and they would be equally spaced at 90 degrees, or pi by 2. Okay, so we're not quite there with what we need to do just yet, but we can take it a little bit further and find the square root of an actual complex number rather than just using this rule. The square root of an actual complex number, but it needs to be written in polar form. So you need to put it in polar form first. And you can use your calculator. This time I'm just going to do it in degrees, so your calculator will be in degrees. So it would be shift the plus sign, then negative 7, 5. I don't want you to write the decimal version of the R value, of the modulus value. I would actually like you to find that. So that's negative 7 squared plus 5 squared. So that's 74. So it's the root of 74. But you can just write down, if you're in degrees, that the angle of theta is approximately that. Okay, so all we've done is we've rewritten negative 7 plus j5 as a polar form, in polar form. But we want to take it to the square root. We want to take it to the power of a half. So let's continue. We've now written it as root 74 angle 144.46. And we can rewrite that as that to the power of a half. All right, using the rules on the previous page, that would be, now, root 74 is already 74 to the power of a half, so taking the square root of that, it becomes 74 to the power of a quarter, angle 144 over 2. That's one root, and because there are two roots, they're equally spaced by 180, so the next one will be same length, angle 144.46 over 2, but a further 360 over 2 further round. So we could do the arithmetic. At this stage, we can find the decimal version of 74 if we want to. I think it's about 2.94. So 144.46 over 2. And the other one, same length, but a bigger angle, obviously. Or you could have done it back into rectangular form, just using a calculator. Okay. If you're using this to answer a MyMathLab question, just be guided by how MyMathLab wants you to answer it. We also need to be able to find roots if it's written in a different format. But the same thing will apply. We'll still need to put it into polar format, polar notation, so we can do that. That's a fancy way of writing what we're about to do. Find the cube root of 8 cos 120 plus j sine 120. Okay, z equals 8. That's straightforwardly 8 angle 120. That's just one of those ways of writing it. Okay, so we need the cube root, so that's z to the power of a third. So that's going to be 8 to the power of a third, angle 120 over 3. 8 to the third, angle 120 over 3 plus 360 over 3, which would be 120. And the third root would be the same to start with, but we're going to add 120, and then we're going to add another 120. Okay, tidy it up if you wish. The cubed root of 8 is actually 2, so we could write it like that. 120 over 3 is 40. Then 2 angle, the next one is going to be 40 plus 120, so that's 160. The next one is 2 angle, add on another 120, that would be 280 degrees. Then we could, if we're required to, draw them, and we draw them in a circle with the axes in the middle. Oh, that's not in the middle. Right, the first one would be 40. The next one would be 160, so it's about there. And the last one is going to be there. Now, my circle's not very good. So they're equally spaced at 120 degrees each time. Next one, we're going to find the fourth root. Same deal, convert it straight away to polar. and then off we go. Z to the power of a quarter equals 7 to the power of a quarter angle 80 over 4. 7 to the power of a quarter angle 80 degrees over 4. Now this time we're going to add 90. It's in degrees, so 360 divided by 4 is 90. The next one will be the same length, 80 over 4, which obviously we could write as 20. So plus 90 plus another 90. And the last one would be 80 over 4 plus 90 plus 90 plus 90 degrees. And obviously you would tidy all of those up, but those are 4 roots now, each of them being 90 degrees apart. So if you've got your circle, and the first one was 20 degrees, so it's pretty little. The next one is going to be at 110. The next one's going to be at 200. And the next one's going to be at 290. Like that. So they're all 90 degrees apart. We can do the same with a root that's not 1 over something, and we can do the same if it's a negative fraction as well. Have a look at this one. Okay, we'd need to change it into polar form first, but we also should note that we've got 3 roots. So negative a half plus j half is going to equal 2 to the negative a half, or 1 over 2, square root of 1 over 2, angle 1 over root 2. Oops, no, that's not what I meant to say. That is not what I meant to say. What I was saying was that 2 to the negative a half is 1 over root 2. That's what I was meaning to say. But also that the angle is 135. And again, I'm just using degrees, so that's fine. So now I need to take the power of negative 2/3 of 2 to the negative a half, angle 135. Okay, just using the rule, that now becomes, right, 2 to the negative a half to the power of negative 2/3, angle 135 times negative 2/3. Same again for the power. And then the first angle plus 120. Because there's 3 of them. And then the last one is going to be the same length. And then it will be plus 120 plus 120, so it'll be plus 240. And we can tidy all of that up. 2 to the negative a half to the negative 2 over 3 is equal to 2 to the power of a third. Angle, the first one is negative 90. The second one is the same length, but angle 30. It's 120 difference. And the last one, 30 degrees plus 120 is 150. Now we're going to put all of this together, and we're going to do something like find cos 4 theta. Sometimes the question might be like, show cos, so an alternative question, show cos 4 theta equals 8 cos to the power of 4 theta minus 8 cos squared theta plus 1. So sometimes it just says find cos theta, or sometimes it says this is what you need to get to. Okay, so for an ordinary standard random complex number, z to the power of 4 equals, from the earlier, I think from slide 3 or something like that, it says cos 4 theta plus j sine 4 theta. Now remember, I'm going to now work this out because z is cos theta plus j sine theta to the 4, and I would be using Pascal's triangle to work it out. I'm also just going to abbreviate it, if you like. I'm just going to use C for cos and S for sine. So I'm just going to expand this. So plus 6c squared js squared plus 4c to the 1 js cubed plus 1 times, I don't need the 1, js to the power of 4. Now we remember that j squared is negative 1, j cubed is negative j, and j to the 4 is 1. So I'm going to incorporate that. So, and I'm just going to put my j out the front. The next term has j squared in it, so that means j squared is negative 1, so it's minus 6c squared s squared. Excuse me. Okay, j cubed is negative j, so it's minus j times 4c s cubed, and then j to the 4 is 1, so it's plus s to the power of 4. Okay, let's go back and let's use some colour. Let's use let's use blue to match the imaginary bit. So there's a blue, and well, actually maybe I should tidy it up before I get to that stage. So maybe I should go a little further and put the reals first. And then take out a common factor of j. So I've got the first term 4c cubed s minus 4sc cubed. So now I'm ready to match the imaginary part of what we've expanded. It's there. And I need to match up the real part with the real part. Okay, the pinky bits are the real parts, and it just so happens that the first pinky part is cos 4 theta. So cos 4 theta equals cos theta to the power of 4 minus 6 cos squared theta sine squared theta plus sine to the power of 4 theta. That doesn't look like where we're going. But remember, sine squared theta is the same as 1 minus cos squared theta, so I can start filling that in. And if I look at where I'm supposed to be heading, all of my answers all of the bits are in terms of cos, so I need to change sine to the 4 theta into sine squared theta squared, and sine squared theta is 1 minus cos squared theta squared. Nearly there. So now we just need to get rid of those brackets. Okay, 6 cos squared theta times 1. Then minus minus gives us a plus, and that's 6 cos squared theta plus, and then I need to multiply out this bracket, and then I would get 1 minus 2 cos squared theta plus cos to the 4 theta. Okay, tidy up time. I've got cos to the 4 theta plus 6 cos to the power of 4 theta plus another cos to the power of 4. So that's 8 cos to the power of 4 theta. Then I've got minus 6 cos squared minus another 2 cos squared, so that's minus 8 cos squared theta, and everything's gone but the 1. And yes. Now, if you didn't have some required format, like this question gives you cos 4 theta equals blah, blah, blah. If you didn't have that, then the very first line where it says cos 4 theta equals cos to the power of 4 theta, etc., that would be correct. It would be considered correct, as would the next line, But in this case, it asked you to find what it was in terms of how the question was worded. So we just had to keep on going until we could find it. Here's another one. Only this time it wants you to find cos cubed. Okay, so remembering the same thing, sine squared plus cos squared is 1. The question could have been find cos cubed theta, or show that cos cubed theta equals a quarter of cos 3 theta plus 3 sine theta. So it might be written like that. Okay, so now we remember that z cubed equals two ways, either cos theta plus j sine theta cubed, or that it's equal to cos 3 theta plus j sine 3 theta. Now all we have to do is make the sides equal by expanding the first bit, because we can expand that, and then we pick out what it is we need. So we're going to expand the left hand side, and again I'm going to use c for cos and so on. So that would be c cubed plus 3c squared js to the power of 1 plus 3c to the power of 1 if I need to write it in, js squared plus 1 times js to the power of 3. And remember, j squared equals -1 and j cubed equals -j. Okay, bearing that in mind, we can write that as c cubed plus, I'm going to put the j out the front, j squared is -1, so that would be minus 3cs squared. J cubed is minus js cubed. I also now want to collect up, and I may as well write back in full the real terms and the j terms. So my real terms are going to be cos cubed theta minus 3 cos theta sine squared theta. Then take the j out as a common factor. And then minus sine cubed. Let's use colour again. Let's use pink for the real bit. So this must be the real bit, which corresponds to cos 3 theta. And then the imaginary bit is the sine 3 theta, which must be that bit. So matching up those two bits now, we can say that cos 3 theta must be equal to cos cubed theta minus 3 cos theta sine squared theta. Not quite what we're heading for, not quite what we're hoping for, but if we just remember that sine squared theta is 1 minus cos squared, we're going to be a lot closer. Getting closer. Now multiply out the brackets. Okay, not there yet, but let's tidy that up. We've got minus minus gives us a plus. So we've got 4 cos cubed theta minus 3 cos theta, and that's equal to cos 3 theta. All right, all we have to do is we're looking for cos cubed, so we could say by rearranging this that 4 cos cubed theta is going to equal cos 3 theta plus 3 cos theta. We didn't want 4 cos cubed theta, we only wanted cos cubed, so we could say that cos cubed theta equals, okay, divide both sides by 4. I think my original thing should have said cos, because that wouldn't work. There we are. Now we've got, once we corrected that up above, then we've got what we needed to get. So that's how you can, in effect, create your own trig identities. What is cos cubed theta? It is equal to a quarter of cos 3 theta plus 3 cos theta. Next slide. We can simplify this straight off by just getting rid of the inner brackets. And then recognizing that it looks very similar to sine A plus B, which is equal to sine A cos B plus cos A sine B. Or the other order, it doesn't matter. Now we also know, we did this earlier, that cosh of j times something, x will do fine, is equal to cos x, and that sinh of the same angle with a j in it in there, so this expansion, look, we've got j times something there, is going to be j sine x. So I'm going to go ahead and expand this. So it's going to be just following this, but plus the h's. This is Osborne's rule. We talked about that too. Okay, so now it's the same rule, but we're just going to have sinh instead of sine. So it's going to be sinh hyperbolic sine pi by 3 cosh j pi by 3 plus, now it doesn't matter whether I do cosh pi by 3 sinh j pi by 3 or the other order, doesn't matter. So now thinking about this, sinh, that's fine, we can look up this on the calculator. We need the identity to find what cosh j is. Cosh of j is just straight out cos, and sinh of j, the j comes out the front, and then we've just got left with cosh pi by 3 sinh pi by 3. Whoops, might have got a bit carried away with my h's there. Sinh j, as we've got up here, is j sine, so we'll just take that out. Now, all we have to do is, with our calculator in radians, we have to just look up sinh of pi by 3, multiply it by cos. Now, I did find that when I'm doing this on my calculator, you really have to do that. Otherwise, it gives you some crazy answers. Okay, so then you should get that the first term is 0.6247 plus j times 1.3859. That's from your calculator. The last question I want to do, no, second to last question I want to do, is where we've got an expression z squared equals 3 plus j, and we need to find z. So this says find z. So z is going to equal the square root of that. And in order to find the square root of that, we have to find 3 plus j in polar terms. So we would find that that would be the square root of 3 squared plus 1 squared, that's the square root of 10 angle, and we can look that up on the calculator, and we'd get 0.32175. Okay, right, so now that is z squared, so z is going to be that to the power of a half. Now 10 is already to the power of a half, so we'll just become 10 to the power of a quarter angle that. Now we're finding the fourth root. No, we are finding the square root. So it would be that number divided by 2 or multiplied by a half. And then there'll be one more square root. We're talking, let's talk radians. So it's going to be pi further on. So let's have our calculator in radians. So then it would be, the second one would be 10 to the power of a quarter angle a half times that plus pi. And then you'd work out your numbers, and it will be, you know, the same thing. They'll be equally spaced by pi around your circle. The last question is a quadratic. It's a complex quadratic. Okay, and what do we use to solve quadratic equations? We use the quadratic formula. So we need to write out what A is, what B is, and what C is. Then we just fill it in. So Z is equal to the opposite of B plus or minus the square root of B squared minus 4 times 1, I don't need to put that in, times C, all divided by 2 times A, which is 1. Now, if we expand the brackets under the square root sign and subtract off 20 plus 4j, we get negative 2j minus 3 plus or minus the square root of negative 15 minus 8j, all over 2. Now, this has got the same kind of idea as we've had before. We've got 2 square roots, so it's plus or minus. It's not quite, but it's that idea. So we need to find the square root of first, that negative 15 minus 8j. Okay, we do it in exactly the same way as we did for the previous ones. We'd need to change it into polar first. Now there's just a little bit of polar, a little bit of a trick with this polar conversion. You would get you would get 17, and then you might get the negative number. You might get that it's negative 2.6516. All that means is it's going around the circle that way, which is wrong, so to speak. So we need to, instead of having that, I don't suppose I need a circle, but instead of having about, I think it's about here, going that way, I need to write it going that way. So it would be 2 pi minus 2.6516, which is equal to 3.63155. All right, I'm just renaming what you get on your calculator because I just want to get rid of as many negatives as I can. So that then becomes 17 angle 3.63155. And I'm going to take that to the power of a half. Okay, so it's going to be 17 to the power of a half angle 3.63155 over 2, and then another one 17 to the half angle 3.6 over 2 plus pi, because there's 2 of them. You would need to change those back into rectangular form. You need to change them into rectangular form because you've got to add them to that negative b. So you'd need to change them back. So the first one becomes negative 1 plus j4, and the other one becomes 1 minus. So that second root was 1 minus j4, which you can see is the opposite, but we have to work it out. Then we put those back in as a replacement for the square root sign above. And then we work it out. Now, I'm not going to finish it because I'm pretty sure this is an assignment question, but you would then sub this back in to the square root bit up here. And then we're done. Okay, thanks for watching.